All right, so let's continue on with the chapter 3, and we had talked about strong acids and the pKa tables and everything that you needed to learn. Okay, and so we talked about how we use pKa in organic chemistry usually instead of Ka values, because Ka values tend to be really inconvenient to use with the 10 to the negative 50, 10 to the negative 7, 10 to, and so it's generally much easier for us to deal instead with negative log of the Kas. And remember, we said the strongest acids have the lowest pKa values. The strongest ones that we deal with have pKa values less than 0. Okay, and the weakest acids, and that would be pretty much anything with a hydrogen that is not acidic, something that you would never consider acidic, like methane, CH4, for example. You would almost no one would call that an acid. Its pKa will be on the order of about 50 because it is so non-acidic. All right, so here we have again a generalized list. This is out of the book, fairly similar to what I asked you to learn there. And on the inside of the textbook, there's an even more comprehensive list. And also on my website, I gave you a more comprehensive list of things to measure as far as these go. And remember, I'm usually more interested in knowing to the nearest 5. So for example, if I asked you the acidity of this guy right here, I would expect you to memorize that carboxylic acids are about 5. Remember, we learned that, right? We learned that phenols are about 10. Alcohols are close to 15, although clearly they can be over a range. Water is 15.7, ethanol 16, tert-butanol 18. So, but in general, they tend to be close to 15 with variations. And then there's other groups here that we did not learn. For example, I said amines 40. 40 is close enough. I think it's much easier to memorize to the nearest 5. All right, so let's take a look at these guys here. Which one of these acids is stronger according to this list here? Hydrochloric acid or sulfuric acid?
Hydrochloric.
Remember, the more negative, the stronger. Here's hydrochloric.
Sulfuric.
So sulfuric is the strongest on this list. It's -9. How much stronger? How do we compare those numbers?
Is it 30 times stronger?
No, because remember, it's orders of 10. So it's 10 to the 2. If the difference is 2, it's 10 to the power of 2. Because remember, these were logarithms before. We took logarithms of these. So it's not 2, but 10 to the 2. So I would say sulfuric acid is 100 times stronger than hydrochloric acid. Okay. And similarly, if I was to compare, let's say, ethanol and isopropanol, T-butanol here, 16 to 18, ethanol is 100 times stronger. Okay. The difference is 2, so it's 10 to the 2 difference. But that's not usually a question we worry about much. But I just want you to understand again that these aren't, you can't say this one is twice as acidic. That doesn't really make sense most of the time. It's 10 to the power of something if you're going to compare them. What do they have? What does a pKa of 5 mean, for example? If something has a pKa of 5, remember, then what is its Ka? pKa of 5 would mean its Ka is what? Remember this equation here? So if the pKa is 5, then the Ka would be 10 to the -5. Okay, it's the anti-log of that. So if the pKa is 5, the Ka is 10 to the -5. And what that means is for every 100,000 molecules, only one of them dissociates. That's essentially what that means. Because 1 to 10 to the 5, 10 to the 5 is 100,000. Those are what those numbers generally tell us. If you have a Ka of 1, that means that, you know, for every, basically, I think the best way to think about that is for every 2 molecules, one of them dissociates, so that you have an equal number on both sides. Now, extremely important is to understand the relationship of the acid to its conjugate base. Sulfuric acid is an extremely strong acid. It dissociates completely in water, as we see here. I know it says -9, but pretty much anything under 0 we say is strong, and it completely dissociates. What that tells me is its conjugate base. If this is one of the strongest possible acids, excuse me, this is among the weakest possible bases. Basically, you want to think about it like this. The hydrogen and the hydrogen sulfate ion divorce. They separate. How badly do they want to get back together? For a strong acid, not at all. Okay? What this means is this ion is perfectly stable in solution. It is incredibly stable. It does not need that hydrogen back at all. It's not going to go searching to pull it back. It's very content like this. Same thing with HCl. You dissolve this in water. pKa of -7 means extremely strong acid. Okay? So this is going to lose its H. And how badly will the chloride go looking for an H plus to get back, so to speak? It won't, right? Remember, if we go back to Chem 140, we said that these ions are neither acidic. Well, this one's a little tricky because it's still a little acidic because of that hydrogen. But this chloride is a totally neutral ion. It is not at all basic. You put chloride in solution, if the pKa of the water is 7, you add, if the pH of water is 7, you add chloride ion, it's not going to change the pH at all. It's not a base. It doesn't try going for hydrogens. That was kind of the definition of strong acid, is it dissociates completely in water, and it's not going to, you know, its conjugate base doesn't want the hydrogen back. So very important to understand that. The strongest acids produce the weakest conjugate bases. Ammonia, do we ever think of, what do we think of ammonia as? An acid or a base most of the time?
Base.
A base, good. But on this table, it's listed under acids. Okay, right now it's an acid. It has a pKa of 38, which means it is an extremely, extremely weak acid. Almost no one would ever consider this an acid. But it does have a hydrogen, right? So could you consider it an acid? So long as it has a hydrogen to donate, it's potentially an acid. But it's way down towards the bottom among the weakest. So what does that tell you about this ion here, which is called the amide ion? That's confusing because we already have used the word amide for something else. But this is called the amide ion.
It's a strong base.
It's a very strong base. Yes, it is a very strong base. Because if this is an extremely weak acid, this must be a very strong base. Okay. And then on the other extreme, if this molecule here, ethane, is among the weakest acids, that means its conjugate base is about as strong a base as you're ever going to get. Does that make sense? So the weaker the acid, the stronger its conjugate base. If I wanted to remove this hydrogen, what would I use to remove that hydrogen? I would use a base like I certainly wouldn't use chloride, right? It's way too weak. I'd have to use something down here to remove that hydrogen. Does that make sense? So I need something that's a much stronger base than this was an acid. So if I use this ion right here and I add it to ammonia, because this is such a strong base compared to this, it will remove that hydrogen and give me amide ion. So that's how we compare these. The stronger acids towards the upper left corner, the weakest bases, excuse me, the strongest bases, the lower right-hand corner. Okay, so what we're going to want to be able to do here is compare a reaction and figure which side the equilibrium favors. And in general, the way this will go if we're dealing with pKa's is we should always have the arrow pointing from the lower pKa value to the higher pKa value. Okay, so let's think about this here. We have the conjugate base of an alcohol plus water. This is going to go ahead and deprotonate. Let's go ahead and draw in arrows for this. If I wanted to draw the curved arrows, where would they be going?
From the acid to the base?
No, 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 never.
Or from the base to the acid?
Yeah, it's always from the electrons towards what they're going after. So this would be like partially positive, wouldn't it?
Yes.
Okay, so the electrons would be going, sorry, that's ugly, ugly. Let me zoom out. Okay, so the electrons would go to grab that hydrogen. And now hydrogen would have two bonds, not allowed. So these electrons would go to the oxygen. Remember, this is a reaction, not resonance. So you are totally allowed to break that bond. So this arrow means you are making a new bond between oxygen and hydrogen. It is using its lone pairs to become a bond. And this arrow means that these electrons in the bond go to the oxygen. This is called heterolytic cleavage. All of the acid-base reactions work this way, okay? Which is the base uses its lone pairs to grab the hydrogen lets go of the electrons in its bond to that atom. Okay. Conjugate the reaction going backwards would be what? This oxygen would want to grab back the hydrogen and put those electrons on the oxygen. The equilibrium is going from the lower pKa value to the higher. The way you compare these is you always compare the acid and the conjugate acid. Which one is stronger, the acid or the conjugate acid in this reaction?
Acid.
The acid. So it should always point from the stronger acid towards the weaker acid. Okay. If the numbers were reversed, if there was, say there was a 20 here on the left and a 10 here, the arrow would point from the stronger acid to the weakest. It would go the other way. Okay. In the next problem set, which I'm putting together, you'll have questions like that where I say, you know, here's the acid, here's the base, draw the products, and then tell me which way it's going to want to go, to the right or to the left. Always from the stronger acid towards the weaker acid. The other way you could do this is from the stronger base towards the weaker base, because which is the strongest base? This is. But we don't memorize pKa values. But just be aware, if you can't figure out the acids, you could do it by bases as well. This is the stronger acid, and this is the stronger base. It should always work out that way. The stronger acid, the stronger base, with the weaker acid and the weaker base. Okay, so what does that mean when the equilibrium arrow is bigger? That means the reaction favors the right side. Okay. if you remember, what would the K value be here? It would be 10 to the 18 minus 15.7, which is 10 to the, and I'm not going to ask you this on an exam, 10 to the 2.3, which is what? 10 to the 2.3 is, it's basically 200, roughly, or 1.99 times 1. Yeah, it's 2.0 times 10 to the 3. 10 to the 2. Okay. Now for me, for all intensive purposes, if the difference is less than 6 between these, I will consider that an equilibrium. Because if the difference between these is less than 6, then the K values would be somewhere between 10 to the -6 to 10 to the +6, right? Anything between there, I will consider equilibrium. Anything out of that range, I will usually mean the arrow goes completely to the right or completely to the left. Okay. Beyond 10 to the 6, the reaction goes completely to the right. And if it was less than 10 to the -6, it would go completely to the left for all intensive purposes. That's going to be important when we get to mechanisms, because if there's an equilibrium, then you could go either way. And then Le Chatelier's principle will play into that as well. We'll review Le Chatelier's principle in chapter 6, but that term should be familiar. Okay, so let's look at this reaction here. This base is outrageously strong. Why do I know this is such a strong base? Look at its conjugate acid. Its conjugate acid is the weakest kind of acid there is, an alkane. There's really nothing weaker than an alkane. So that means if this is an alkane, this is an incredibly weak acid, then that means that this base is extremely strong. Okay. So compare here. Water, which you normally don't even think of as an acid, has a pKa of 15.7. Butane has a pKa of 50. That's a huge difference, 15.7 to 50. That is a difference of what is that, 50 minus 15.7, which is approximately 10 to the 35. Very close to 10 to the 35. That's a huge difference. This reaction goes pretty much only to the right. Okay. There's no equilibrium here. It goes to the right. It will not go to the left at all. That's why I say it's not really much. It's an equilibrium just in the sense that there technically is a constant there. But remember how we talked about strong acids? We said there really is no equilibrium with a strong acid. This is even more so. This is such a dramatic change. So the closer these numbers are, what do you have? You have more and more of an equilibrium. Okay. For example, if I put water with the conjugate base of this, these numbers are so close that the acid, the base, the conjugate acid, and the base will be pretty much entirely in equilibrium. 15.7 to 18, that's close enough that they would be very much in equilibrium. So if you make one of them the acid and the other the conjugate base. Okay. So that's the quantifying part. Those numbers right there. Now, as I said, I wanted you to memorize all these things, these pKa values. I gave you the list. But for right now, I want you to put them aside. I want to understand why. For example, this hydrogen is much more acidic than this hydrogen. So that's a different issue now. Now we're going to why. So if I ask you, why is this a stronger acid than this? The answer I don't want to get is, well, the pKa number is less. Yes, I know that. You know that, I know that. Why is this pKa so much less than here? Okay. Well, because it's on the table. No, that's not an answer. Why? Okay. And that's what we're going to be focusing on right now. Why? Okay. So it's obvious that which of these is the stronger acid, for example, hydrochloric acid or butane?
Hydrochloric acid.
Yeah, hydrochloric acid. Yeah, butane is barely an acid, as we've said. Okay. So we want to figure out which is the stronger acid. And most of the time, the answer is going to be the opposite. We usually want to do this question backwards. Instead of saying which is the stronger acid, what would be the equivalent question?
What is the weaker conjugate base?
Exactly. That's usually the question. Which has the weaker conjugate base? So chloride is a much weaker conjugate base. So those are the two questions, and it's usually easier to approach it backwards. Okay. So a formal charge can have an effect here, but we need to look at why. And so we're going to come up with a system. And your textbook comes up with kind of its own way of doing this, which is fantastic. I really like it a lot. It doesn't work in 100% of the time, but it works a lot of the time. And this is going to be called ARIO, the ARIO system. Okay. The key is to look at things backwards, as I mentioned, and look at the conjugate base. The more stable the conjugate base, the stronger the acid. Okay. So the more stable the conjugate base, the stronger its acid. Hydrochloric acid, the conjugate base is chloride, right? Chloride is a very stable anion, very non-reactive, very inert. Therefore, this is a strong acid. It would like to separate and become chloride ion by itself. On the other hand, this would not like to separate because this is extremely reactive. It is not stable by itself. It really wants that hydrogen back. And so we're going to look at why this is so much less stable than hydroxide. That's usually how we compare these. We compare the base and the conjugate base. Okay. So these are the factors that we will look at, and they are listed in order of priority relatively. Okay. Which atom carries the charge? So we're asking the stability of negative formal charges. Which atom has the charge? Is there resonance to stabilize a formal charge? Is there induction, which we will talk about later? And finally, especially for carbon atoms, what type of orbital is that negative charge located on? An sp3, an sp2, or an sp? And so these will be ARIO, and the importance of the effect is listed in order. So the atom effect is going to be the most important. So the atom effect. Okay. So more electronegative atoms are better at stabilizing negative charge, first of all. Okay. And why is that? By definition, what does electronegative mean?
It draws in electrons strongly.
Yeah, through bonds. Good. It's pulling the bonding electrons. Okay. So if we look at these two compounds, carbon and hydrogen have very close electronegativity values, right? Carbon is not particularly electronegative unless it's bonded to a metal. If it's bonded to another nonmetal, it's really very, very neutral here. So these two are sharing relatively equally. What about oxygen versus hydrogen? The oxygen and hydrogen are not sharing equally. Where are the electrons being pulled to?
Oxygen.
To the oxygen. Oxygen is much more electronegative, and therefore it's much better at stabilizing negative charge than a carbon, right? Oxygen is much better able to accommodate a negative charge, a negative formal charge, than a carbon is.
I have a quick question, Professor.
Yes.
So what exactly is a pKa? What is it telling us, or what exactly does it mean?
Ka, remember,
Uh-huh.
Ka is the negative log of the Ka value for a acid. So you remember Ka values from Chem 140, right? But yes or no? You remember?
Yeah. I remember.
Okay, good. So the pKa is the negative log of it. And so the key to just understand is the lower the value of the pKa, the stronger the acid. Okay. So the higher the value of the pKa, the weaker the acid. So that means sulfuric acid here, which has a pKa of -9. That means its Ka is 10 to the positive 9. That's an extremely strong acid. It totally dissociates in water. This compound here, ethanol, has a pKa of 16. That means its Ka would be 10 to the -16. This does not dissociate in water hardly at all, not much, okay? The reason we do it this way is so that we can compare different acids. It's easy to compare them by knowing their pKa values. So that means if we put them together, we will know which side the equilibrium will go towards. The equilibrium will always prefer for the stronger acid to lose its proton to form the weaker acid, as the case may be. Okay?
Alrighty, thank you.
Yeah. So let's look at some values here for some potential acids. So first, let's look at the top row. These are all hydrides of various elements. So that means I took the element and added as many hydrogens as that element would normally have. So carbon with 4 hydrogens, nitrogen with 3, oxygen with 2, hydrogen with F. Okay. Clearly, on the top row, which is the strongest acid? Methane, ammonia, water, or hydrofluoric acid?
The stronger acid?
Yes.
The hydrofluor.
Good. Hydrofluoric is by far the strongest, right? And which is the most electronegative atom? Carbon, nitrogen, oxygen, or fluorine?
Fluorine.
Fluorine. So this first row should make total sense. Based on electronegativity, fluorine is much better to is a much more stable ion than OH. Okay. Fluoride is much better able to handle the negative charge. It is by far the most stable base compared to hydroxide. Okay. And then we're not comparing hydroxide to ammonia. We would be comparing it to NH2 minus. NH2 minus is extremely unstable. And the only thing that would be even more unstable would be CH3 minus here. That's what this is telling me. Fluoride is much better able to handle the negative charge. Go down to the second row. Which of these is the stronger acid? Hydrosulfuric acid or hydrochloric acid? So hydrosulfuric, H2S, or HCl, which is the stronger acid?
HCl.
Good. Chlorine is much more electronegative than sulfur. It makes sense that chlorine can handle the negative charge better than sulfur could, and so therefore its conjugate acid, HCl, is a much stronger acid than hydrosulfuric. But something doesn't seem to work. What is the most electronegative element again?
Fluorine.
Yeah, now didn't I just say fluorine is best able to handle a negative charge, right? Because it's the most electronegative. But read the table down, though. By far, which of these is the strongest acid?
HI.
HI is much stronger than HF. Huh. Fluorine is much more electronegative. Shouldn't it be much better at handling the negative charge? So the issue comes down to two factors here. There are two factors. When you compare atoms, so for right now, the comparison is only carbon, nitrogen, oxygen, fluorine, and specifically anions. So F minus, O minus, N minus, C minus, Cl minus. If you're comparing those, you compare across groups using electronegativity. The same row, you can use electronegativity. You can't use it within the same column, though. So you can only compare electronegativity if the atoms are approximately the same size. Okay? So I can use electronegativity to compare these four, because fluorine is about the same size as oxygen, is about the same size as nitrogen, is about the same size as carbon. They're all relatively close. Why? Because their electrons, remember, are in what shell? What's the valence shell? These are in period 2, so their valence shell is 2. They're small atoms. Sulfur and chlorine are in the third row of the periodic table. Shell 3, they're bigger. Okay? So you can only compare across a row or a period for electronegativity. But what's hugely different here between fluoride, chloride, bromide, and iodide? They have massively different sizes. So it turns out that even though fluorine is more electronegative than iodine, it's the size that matters when there are different sizes. With fluorine, the negative charge is concentrated in an extremely small volume. With chlorine, the volume gets bigger. Bromine, bigger still, and then iodine, much larger volume. What is this kind of like that we've talked about before that stabilizes charges?
Intermolecular forces?
Not exactly. What we've talked about today, I mean in the last couple days. What makes a negative charge much more stable if you can do what to it?
A complete octet?
Starts with a D.
Delocalize.
Delocalize. Remember, delocalize meant you could spread the negative charge over many atoms? Same idea. If you can spread it out over a much larger volume, then that's going to make the negative charge much more stable. And so this is the two issues that we need to deal with here then. Okay? So electronegativity and size. So electronegativity is comparable if the atoms have the same size, meaning they are in the same period. So atoms that are in the same period, the more electronegative, the better it is at stabilizing the charge. In other words, the more stable it is as an anion. Fluoride is more stable than hydroxide. Hydroxide is more stable than amide. Amide is more stable than CH4. In other words, if I was to write this out, okay. CH3 is the least, minus is the least stable. NH2 minus is less than hydroxide, is less than fluoride. Okay, so these are the conjugate bases. And remember, the more stable the conjugate base, the stronger the acid. The more stable the conjugate base, the stronger the acid. Again, it's like a divorce without all the emotion, okay? HF, can they split up really well? Not really. Fluorine will want that H back, but not nearly as much as hydroxide wants the H back, and not nearly as much as NH2 minus wants the H back. Oops, I'm sorry, and I wrote that wrong. That's not NH2 minus, it's NH. What? It's NH.
2 mono minus.
Minus, thank you. Yeah. Okay. And again, that's because these all have C, N, O, and F are in
The same row.
same period, right? All in period 2. So same size. So different electronegativity, but roughly the same size. And by size, you could mean what? Like the volume, right? The same size of the atom. But if we look at the other way here, fluoride is less than chloride, is less than bromide, is less than iodide. And again, when we're talking about stable, we're talking about in the context of acid base, right? Again, these are all conjugate bases. So these are different sizes. The larger anion is more stable. Regardless of electronegativity. Do we think we get that then? So electronegativity only matters within a row for stability. If we're within a group, within a column, the larger one is the more stable. And you also have to be careful that we're comparing conjugate bases. We're not comparing F minus and NH3, are we? We're comparing F minus and NH2 minus. So you have to take away a hydrogen on all of these. So that is by far the most important factor in comparing these two. So when I ask this question here, which one of these is the more acidic? The answer would be propanol is more acidic because its conjugate base is more stable than butane's conjugate base, because oxygen is a more electronegative atom than carbon, correct? That is an okay comparison because these are both in the same period. Oxygen's in period 2, carbon's in period 2. They're about the same size, meaning the negative charge is stuck over about the same volume. That tends to be the most probably confusing aspect of this. So why is size so important? It has to do with what we call polarizability, okay? So if atoms don't have similar sizes, as I said, larger anions can spread their negative charge over a larger volume. So that's called polarizability. The bigger the volume, you can push the negative charge all over the space, so to speak. So iodide is much larger, more polarizable. So those are the things that stabilize: electronegativity and polarizability. And ultimately, given the choice, polarizability is more important than electronegativity. Okay. So hydrogen atoms bonded to larger atoms are more acidic than those bonded to smaller atoms in the same group. Okay. R. R is resonance in REO. Okay. Sorry, this is from another book, so this kind of summarizes it again. Their values are a little bit different in the way that she's putting it here, but you get the idea. Increasing electronegativity, increasing acidity across a row. And then finally, within a group, the bigger the anion, the bigger the conjugate base, the more stable, so the more acidic that you have here. R. Okay, now I want to compare the next factor. So I need to control A. What do I mean by control A? I want to look at only hydrogens bonded to the same atom. A was atom effects. It was the most important. Now let's suppose the hydrogens are bonded to the same atom. Do you agree, if I'm comparing ethanol and acetic acid, which hydrogen is the acidic hydrogen? In ethanol, it's the one bonded to the oxygen. And in acetic acid, it's also the hydrogen bonded to the oxygen, right? Clearly, acetic acid is more acidic than ethanol, and I can't use atom effects. Why can't I say it's because of the oxygen? Well, because both hydrogens are bonded to oxygen, right? So it can't just be the oxygen. There has to be some other reason why acetic acid is more acidic than ethanol, and this has to do with resonance. So look at the conjugate bases. Compare the conjugate base of acetic acid to ethanol. So compare the conjugate bases. What would we say about that negative charge? Is it localized or delocalized?
Localized.
Good. So the negative charge is localized on one oxygen atom. Acetic acid. And remember, how do you draw the conjugate base? It's just take away the hydrogen, and it's one more negative than it was before. So this was OH, it's now O. Here are the electrons that were there before. And then these are the electrons that were in the bond, right? Oxygen keeps those. The conjugate base keeps those electrons, always. Can you delocalize that negative charge?
Yes.
Yes. So carbon would now have 5 bonds, but I can push these electrons onto the other oxygen. On the top, I have O. Here I now have a double bond. And what about charges?
Minus on top.
Good. So comparing these two, the negative charge is delocalized over two atoms. So that means that it is what? It is, so this is the more stable. Less stable. Less stable means more basic or less basic. The more stable something is, the less it wants to react, right? Something that's stable doesn't need to react. So this is more stable. So that makes it less basic. Okay. Less stable. So this is more basic. So that means if this is more basic, then its acid is
Less acidic.
less acidic. Okay. The more basic the conjugate base, the less acidic the acid. All right, now, what were the pKa's of this? pKa of this was about 16. pK of this is about 5. It's 4.74. So clearly the stronger acid is acetic acid. Acetic acid has the more stable conjugate base, the less basic. And let me add that in specifically. So less stable, more basic. Ethanol doesn't really want to lose a proton. So if you put acetic acid in water, will it dissociate? Remember, it's a weak acid, so slightly, barely. Ethanol, on the other hand, will hardly. If this is barely, then this is essentially not at all. Does that make sense? Yeah, good. Similar argument. Chlorine can exceed the octet rule, right?
Professor, is chlorine the only one that can break the octet rule?
No, anything in period 3 and below. Sulfur, phosphorus, all of those can. Is this organic, though? What I'm drawing right now, is this organic?
No.
No, no. These are not organic molecules. Okay. So chlorine in organic molecules will not make 7 bonds. Which is stronger, HClO4 or HClO3? Let's compare the bases. So I'm going to change these. I'm going to get rid of those hydrogens. What would the base have? If I got rid of the hydrogen, this would be O minus. This would be O minus. Which would be more stable, the one on the left or the one on the right, and why? And remember, we're still thinking about what? Which word are we interested in this section?
The resonance.
Resonance.
Would it be the
That
one?
negative charge can be delocalized on ClO4 minus to how many different atoms?
3.
Total 4. This
Okay.
oxygen, I could push those electrons to this oxygen, and I could do that all the way around. So 4 oxygen atoms could hold the negative charge. This is extremely stable, okay? Which means what about this acid? If the conjugate base is extremely stable, the acid is extremely unstable. It's extremely strong. This is stronger even than HI, I think, okay? Which of these, what about this one? This is also quite stable, but the negative charge can only be delocalized on 3 atoms, right? 3 oxygens. So the more oxygens you have, the more resonance, the more stable. Does that make sense? So this is an extremely weak base, which would make this a very, very, very strong acid. This is a pretty weak base. So this is quite a strong acid, but not nearly as strong as HClO4. Okay. So this is a much stronger acid. Than this. They're both very strong. I would never want to get either on my skin. But if you told me I had a choice, well, no, I want to make sure that's not clear. HF is by far the most dangerous of all of these. Okay, it has nothing to do with the strength. Okay, HF is dangerous for totally different reasons. So I don't want to imply danger. I just want to say in water, this one would dissociate completely. The Ka value of this one, the pKa value is about 0 to 1. Okay, 0 to -1. This one, it's on the order of, I think, -11 pKa, much more acidic. So the more atoms that you can delocalize the negative charge to, the weaker the base, the stronger the conjugate acid. Induction. Very important we don't get this confused with A. Okay. Induction stabilizes a formal charge by spreading it out in a different way. I call this the giant vacuum cleaner effect, the electron vacuum cleaner effect. Let's look at these 2 acids here. First of all, their atom effect are the same, right? The hydrogens are on oxygen on both of them, correct? The resonance would be the same, because if you take the hydrogen off, you can delocalize the electrons to either oxygen, correct? So same atom, same resonance. But what do these 3 chlorines do? they are very electronegative. So they are pulling the electrons in the bonds towards them. So induction is all about nearby atoms, nearby electronegative atoms. So not the atom the hydrogen is bonded to, but atoms that are nearby. Okay. So induction is pulling all of these electrons towards those chlorines. These bonding electrons, these bonding electrons, these bonding electrons, they're all being pulled towards the electronegative chlorines to an extent. Okay. Trichloroacetic acid is much stronger than acetic. So therefore, what is that telling us? Having nearby electronegative atoms increases the acidity. This is an effect where I don't usually look at the conjugate base. I just look at this and go, up, nearby electronegative atoms. That weakens this bond and makes this more acidic. Now, we already did this comparison. We said acetic acid was more acidic than ethanol because of what? Why was acetic acid more acidic than ethanol?
Resonance.
Yeah, it's the resonance stabilization of the conjugate base, right? Acetate ion can delocalize the negative charge to 2 oxygens. Ethoxide ion, that means after you take the hydrogen, it's called ethoxide. The negative charge is only localized on 1 atom. So resonance was the first effect. There's also an induction effect, because for a moment here, I want you to pretend you don't see that. Okay. They look like the same molecule now, don't they? Yep. But all of a sudden I take it away. Oxygen's electronegative. So not only is it going to stabilize by resonance, that oxygen's pulling these electrons away. So that makes this also more acidic. So it's resonance and induction play a role. So induction is nearby electronegative atoms. Having nearby electronegative atoms weakens the bond, makes this a stronger acid. Okay, so there's a number of ways you have to be able to compare induction. First, the compound on the left is acetic acid. Its pKa of all the ones listed here is the highest, which means it's the strongest or the weakest acid on the page. Of these right here,
Weakest.
this is the weakest acid, right? What is the trend that you're seeing here?
The more chlorides being added, the less the pKa value gets.
Okay, good. The more chlorines, the less the pKa, or the more chlorines, the more acidic, right? So the lower the pKa means the more acidic. Agreed? So having 1 chlorine nearby significantly drops the pKa. It makes it quite a bit more acidic. Adding another chlorine makes the pKa go even lower. Not by quite as much, but still. And adding a 3rd chlorine makes the pKa drop even more. You agree it would not be possible to add a 4th, right? You're maxed out. So this is the first thing to notice. The more electronegative atoms you have, the more acidic. The more electronegative atoms nearby, the more acidic. So it's a cumulative effect. Having 3, it causes the acidity to be stronger than having 2, which is more than having 1, which is more than having 0. What if instead of chlorines I did bromines? It would still have the same effect. Okay, not as much because bromine isn't as electronegative as chlorine, but the more of them that you have, stronger. Here's another trend. Iodine is barely electronegative. It's not really very electronegative, but somewhat. Okay, same concept, except this compound is acetic acid. You might be able to guess the names of the others. This is acetic acid. This is iodoacetic acid, bromoacetic acid, chloroacetic acid, fluoroacetic acid. By far, which is the most acidic? Well, not by far, but fluoro, right? Why do you suppose that is?
The stronger electronegative atom.
Yeah. And again, what is the one on the left? There still is an atom. These are all CH2, CH2. It wasn't highlighted, but it's hydrogen here, right? So fluorine, chlorine, bromine, iodine, CH2, hydrogen. So hydrogen is, remember, they're equally, hydrogen is not electronegative at all. So fluorine has a greater inductive effect because it's more electronegative. Chlorine's inductive effect is less than fluorine because it's less electronegative than fluorine. Okay. Another aspect. What is the same with all of these? They're the same acid, except with one difference, and that is the closeness of the bromine to the acidic hydrogen. So here's the acidic hydrogen. What happens as the bromine gets further away? pKa goes up, meaning it is less and less and less acidic. So by the time the bromine gets about 4 or 5 atoms away, it's no longer there. So inductive effects are more important the closer they are. Okay, so the farther away the electronegative atom gets, the less the inductive effect. If you got rid of the bromine entirely, the pKa would be about 4.76. Okay. At this point, the bromine's barely even noticeable. It's too far away. So they drop off dramatically the further away the electronegative atom gets. If I did this with fluorines, we would observe the same effect. Fluorine nearby, pKa would be much, much lower. And then as far as it gets further away, the more it diminishes. Okay, so again, comparing these three here, the greater the number of the electronegative atoms, the greater the acidity, the greater the inductive effect. The more electronegative that inductive atom is, the greater the inductive effect, the more acidic. The closer the inductive atom, the greater the inductive effect. Sorry, the closer the electronegative atom, the greater the inductive effect, the stronger the acid. So that was ARI. Okay, now let me ask you a question that confuses a lot of people. I want to compare so Which of these is more acidic? We've already seen this.
One to the right.
The one on the right is more acidic.
Yes, I agree.
Thank you. Which one is more acidic, HI or HF?
HI.
Good. Is this a contradiction? Some people will get really confused by this. They'll say, wait a minute, this one has the fluorine and it's more acidic, but this one has the fluorine and it's less acidic. How is this? Why is this?
Size is still prioritized because of the delocalization that makes it a more stable conjugate base.
It does, but that's generally true. But it's because what are the types of effects that I'm looking at?
The induction.
Yeah, in number one, we are comparing induction effects. Note that both acidic hydrogens are bonded to what atom? What atom are the most acidic hydrogens bonded to? Most acidic hydrogen is
O.
H and H. And what are they both bonded to?
O. Oxygen.
They're both bonded to oxygen, yeah. So they say they have the same atom effects because they're both bonded to oxygen. They have the same resonance effects because we could delocalize the negative charge to both oxygens. So these are the only difference between these two is the induction effects. Fluorine is more electronegative, iodine is less electronegative, but the hydrogen's not bonded to the F, right? The fluorine's several bonds is a few bonds away. Good. In two, what are you
Size, the polarity.
What effect did we call that? In REO, that was which letter? A, R, I, or O?
A.
It was the A. The book calls it atom effects. It's kind of a dumb name to call it, but it works well. So even though F is more electronegative, that's not a question, right? F is definitely more electronegative. Iodine was much iodine is what? Is much larger and more polarizable than fluoride. That's a very important distinction. So it's very important that you compare in order. What atom is the hydrogen actually bonded to? Hey, kitty cat. Okay. And you agree, totally different in 1 than in 2. In 1, the hydrogens are both bonded to oxygen. In 2, the hydrogens are bonded to totally different atoms, I and F. Okay. Does this make sense? And which effect is more important in order? Generally, Ario, it is this order. Atom effects are usually more important than resonance effects, are usually more important than induction. So it's the atom that is more important in number 2. Okay. And then the next one is the most abstract and the most flaky. Okay. The type of orbital that the hydrogen is bonded to can also make a difference. Now remember, the hydrogen itself is always in what kind of an orbital? The hydrogen's electron is always in what orbital? Hydrogen doesn't hybridize. It's always in 1s, right? 1s. So, but the carbon it's bonded to will make a difference. And this is only going to really apply to hydrogens on carbon, okay? We're only going to deal with this for hydrogens on carbon. Hydrogens on carbon generally are not considered acidic, right? They were among the least acidic. But hybrid orbitals with more S character, it turns out, are better able to stabilize a negative charge. Remember on the electronegativity table, we said carbon's electronegativity was 2.5. Does that sound familiar? That's technically only if it's sp3 hybridized. It changes depending on its hybridization. So it turns out that sp hybridized carbon is a little bit more electronegative than 2.5. We're not going to come up with a number. Okay. And sp2, not quite as much as sp, but because of their kind of short, stubby nature, I know that seems strange, that would make them more stable, able to stabilize a negative charge. But SPs are experimentally shown to stabilize a negative charge better. S character, being able to spread it out over a more circular space or spherical space, turns out to be better. And so that's going to explain these 3. Okay. So the big difference here between these hydrogens, so just pick a hydrogen, any hydrogen, okay? These hydrogens are all bonded to an sp3 carbon, correct?
Yes.
And these hydrogens are all bonded to sp2.
2.
And you'll notice that these hydrogens are all very non-acidic, right? sp3 more so than sp2. But then it drops dramatically when the hydrogen gets to an sp carbon, okay? This is going to be critically important later on when we study these reactions. Acetylene, this is called a terminal alkyne. Terminal alkyne means carbon on this side, hydrogen. The hydrogens on terminal alkynes, are these very acidic, 25? By comparison, yes, but in reality, that's much, much less acidic than water, right? Water is way more acidic than acetylene. But whereas you need an unbelievably strong bases to deprotonate these, it's not as hard to deprotonate acetylene. What would you need to deprotonate acetylene? What base would you need? Let's see if we can think about this here. Would hydroxide work? Would hydroxide work? Here, let's see if we can compare. Will hydroxide deprotonate acetylene? How do we know? It's very simple. We write the equation. What would the products be? Yeah, that's hard for you to say in words. It would be acetylide ion. That one's, you probably don't know the name. That's fine. Plus what? Plus what? When OH picks up a proton, it becomes
Water.
water. Very good. How do we decide which way the equilibrium goes? Compare the
Conjugate base.
the pKa of the acid and the conjugate acid, or the base and the conjugate base. It's easier to do the acid and the conjugate acid because I know this. What's the pKa? pKa is written right above there. It's 25.
Mhm.
What's the pKa of water? 15.7. Which way is the equilibrium going to go?
To the left.
Yeah, way to the left. So does this work? Now, even hydroxide won't work. Hydroxide is probably the strongest base any of you have ever used, right? So I need something stronger than hydroxide. Any idea what would work? I don't have the tables here. So hydroxide, you agree that's water, right? You're comparing here. Its conjugate acid is 15.7. So that's not going to work. Because if acetic acid, if what's it called, acetylene is here at 25, this one's conjugate base isn't going to work. Where am I going to have to go looking? Will looking anywhere on this side work?
No, in the bottom rows.
Yeah, I need to go below, right? So what would be a good base? Would NH3 be a good base? No. NH3 would be a terrible base because you got confused. Remember, we weren't comparing water. We were looking at hydroxide. It's not H2O. It was OH minus. So it's not NH3. It's NH2 minus that you want. Okay? It's NH2 minus. You have to be very, very careful about these things. So that doesn't work, but this will work. Ooh, I just realized I can use lines for H, but I can't use them for C's. There we go. So this stuff right here, remember, its name is Amide Ion. It's usually made by adding sodium to liquid ammonia. Okay, sodium metal, and that would give you sodium amide. Okay. So plus what? What's the chemical?
NH3.
NH3.
Yeah, NH3. Good. Now we label the pKa's. pKa is 25. This pKa is about 40, right? I think the table I just showed you said 38, but 40 is more than close enough. Now, which way is the equilibrium going to go, if there even is an equilibrium? This one will go very far to the right. Yeah. Incidentally, why does this not work? In case you were adamant about ammonia. let's see here. If you were adamant about ammonia, that would have been NH3, right? What would be on the right side now? Not NH3. What would be on the right side? NH. What's that?
So
4 plus. What was the pKa of ammonium? It's about 10. So clearly, which way would the equilibrium go if that's about 10?
To the left.
Yeah, to the left, way to the left. So ammonia wouldn't work. So ammonia is probably your best weak base. Hydroxide is your best strong base that you learned about in Chem 130, but neither of them were strong enough to do this. You need a really strong base. You need amide ion. Okay, so that's another thing here. So this is going back. We did talk about this earlier in the lecture, but it doesn't hurt to talk about it. But remember, so basically, if you wanted to protonate this, which has a pK18, what do you need? You need the conjugate base of something down here. Does that make sense? And probably not this, because it's too close. Okay. By the way, don't do overkill. If I wanted to protonate an alcohol, I'm usually going to use hydride, sodium hydride. Sodium hydride. Why? Why would I use sodium hydride? Well, let's look at the pKa table. This is not going to be cheaply available. Okay, you don't make bases out of these just for fun of it. That's something you wouldn't know, but you wouldn't do that. Okay, hydride would be great because the pKa of hydrogen is 35. Alcohol is 15. And also, why is this great? What will the product be? Once it's removed the hydrogen, what is it formed? So NaH, so H minus takes away the hydrogen. What does it form? It forms hydrogen. And what's that hydrogen going to do?
Water.
It's a gas, so it'll get sucked up and it's gone. And you can't form an equilibrium if this escapes, right? Once the hydrogen's gone, it's gone. It can't come back. It's a gas. All right. So would I use an alkane, a deprotonated alkane to do this? No, that would be overkill. Does that kind of make sense? You need something that's going to be quite a bit higher, but not way too high. All right. If I want to deprotonate phenol, what am I probably going to use?
Water.
Not water, but you're close. The conjugate base of water. Hydroxide. Right? I'll use hydroxide. I don't use water because what would happen? I would get this, hydronium. And what's its pKa? It's 0. So that would not work. Water wouldn't work, but hydroxide would. Remember, you're comparing an acid and a conjugate acid. Not an acid and a base, but an acid and a conjugate acid. Okay. What would ammonia be good at deprotonating? NH3. It would be good at deprotonating carboxylic acids, right? Because here's ammonium, the conjugate acid of ammonia. Ammonium is right here. So ammonia would be good at deprotonating carboxylic acids. I would not use sodium hydride because it's so far away that the reaction would be incredibly violent and probably cause a fire. Okay. Even with alcohols and sodium hydride, fire is a big risk. And that's the only fire I've ever caused myself accidentally, was sodium hydride plus an alcohol. So what do you have to do to keep there from being a fire? What would you guess? What do you need to do to the alcohol to keep there from being a fire if you add sodium hydride? How do you make something as least reactive as possible? Any guesses?
You add a base?
No, because you're already doing that. And that's what's going to cause the problem. You make it as what as possible. To make something as low reactive, you make it as
Stable.
by putting it in ice. You cool it down. Okay. The lower the temperature, almost always, the less reactive. Okay. So anyway, just so you know, just thinking ahead, this is going to be chapter 6 when we get into, remember, delta G equals delta H minus T delta S. You've all heard of that. Yeah, we're going to get into that more. But we know the lower the temperature, the less spontaneous. So it'll be a little bit better. Okay. I think I have a mistake on that question right there. Should there be a hydrogen there or no? No, I guess not. Okay. Let's say we take this compound here, the way it's written. What is the most, there are, first of all, I think we can agree, there are no protons anywhere here that are considered very acidic. What is the one most acidic proton in this entire molecule? And even that, as I said, is extremely non-acidic. First of all, the alkyne, you would look at the alkyne, right? Are there any hydrogens bonded to this alkyne? No. A lot of people would say, oh, but Professor Petroulis, you meant this hydrogen, right? But if you said that, then what did you do? Is that a hydrogen?
No.
Oh, no.
Carbon.
Carbon.
That's a CH3.
Mhm.
Yeah. What is the hybridization of that carbon?
E3.
Yeah, that's sp3. So if it was a hydrogen, it would have been the most acidic, right? If I change the problem to that being a hydrogen right there instead of a CH3, then that would be the most acidic. But it's not a hydrogen. It's a CH3. So what is the, are there any, so there's no sp hydrogens. Are there any sp2 hydrogens, hydrogens on sp2 carbon?
There's one.
Where?
Like it's by that double bond.
Right there. Yep, very good. It's right there. That is the most acidic hydrogen on the molecule. Okay. What is the pKa of that one? That wasn't one you had to memorize, but it's about 45, right? So the pKa is about 45. What is the pKa of pretty much every other hydrogen on the molecule? Every other one is about 50, right? Would a very strong base be required? And the answer is why? Because pKa 45 corresponds to extremely weak acid. We will take a break in just a minute. Well, at this point, I need a bigger word than very.
Incredibly.
Yeah, incredibly strong base would remove it. The examples would be these two. You would use either methyl lithium or T-butyl lithium. Okay. Remember, that's because their conjugate bases, or pKa of the conjugate acid, is about what? Replace the lithium with a hydrogen, and it would be what? About 50. So that's the only way this would work. And the only way you can even make these in the process isn't by acid-base reactions. You have to use redox reactions to even make these. Okay. This is the strongest base we will ever talk about in this class. There's no way I will give it to you. Sorry, and I'm missing a 3. I don't know if you're aware about this, but a student at UCLA was horribly killed with this stuff. She got it on her coat and just burst into flames, and it's just awful. The professor, managing professor, is, I think he was acquitted, but of manslaughter, but she was not properly trained. I've never even used this. I use this, but I've never used this. And I would use that with a lot of fear. Again, knowing people can be horribly burned to death with it because it's basically stored in gasoline. Okay. So it's very, very, very dangerous. Okay, so that's enough today about REO. So we'll review REO a little bit on Wednesday, and then we'll talk about where it doesn't work. Okay. And then the final thing that we will look at is more about equilibrium positions, more about what's a good acid, what's a good base, some solvation stuff I didn't realize, and then finally Lewis acid, Lewis base. I would recommend reading ahead to just this small section real quick, because in the problem set I'm going to post, I asked some about Lewis acid, Lewis base. We talked about this last semester in 150, but for all of maybe 3 minutes. And we'll only talk about it for maybe 3 minutes this semester too, but we'll talk about it a lot more later.